Hello, my name is Andres Quast. I'm in Physics 2211, and I'm in W14. Today, I'll be talking about Lab 2, Motion of a Falling Object. The purpose of this lab was to apply Newton's second law, the momentum principle, and to analyze, using computational models, the effect of drag on an object in motion, more specifically falling. To observe and track said object using a software that enables us to analyze the minute details of drag. The principles of physics used in this lab were Newton's first and second law, which, as shown on screen, can be Newton's first law can be described as force is equal to the change in position over change in time, and Newton's second law is force equals mass times acceleration, which can be derived in many different ways. And in addition, we use the position update formula, which is shown along with the velocity update formula. So a conceptual model of the drag formula and the net force formula that we'll be using is shown on the right. We can see the paper ball, which is the system that I use in my equation, shown by pushing up with drag force, which in this instance is modeled by air resistance, and weight, which is mass times gravity, which we know, or which we can find using the mass of the paper ball and the constant of gravity from the Earth's gravitational pull. On the left, you can see the drag formula. Force of drag is equal to the negative b times v squared, where b is our coefficient that describes the air resistance. The weight formula, or FW, or the force of weight, is equal to mass times gravity, which we already talked about. The findings of my experiment and observations were the difference between the computational models and with and without the drag, and the exemplified impact of B, like I talked about the coefficient of air resistance. The observed data did not show the exact same numbers as the computational model. This is likely because of some possible differences because of user error. Here is a quick GIF of my dropping, or my video. Okay, the setup of my system was, or the setup of my experiment was a paper ball, and the surroundings being Earth and the atmosphere, that which generate gravity and air resistance respectively. The initial velocity was of the paper ball, which was at rest, was obviously 0, 0, 0, and the initial position was the origin of my graph, which is also 0, 0, 0. The average velocity is the final velocity because the net force is not constant, and the paper ball clearly moves in the negative y direction. So potential errors, as discussed earlier, were seen in during the drop, the paper had uneven folds, which could generate differences in air resistance as the paper ball would spin in midair, which obviously generates different amounts of air resistance. In addition, during analyzation, the tracker data could have been off due to misplacement of data points and the blur of the camera, leading to inaccurate data points, but in the end, it would all even out as the final position is able to be closely calculated. So the software used, first one here was Tracker, and on the left you can see a description that is given by their website, and on the right you can see a visualization of what I did during my experiment. Additionally, we use GlowScript, which is a web-based programming environment that enables students to model 3D situations. So on the left you can see a little bit more of a description, on the right is just a quick picture of it. More specifically in GlowScript, here is my code. To begin with, we have my initial velocity and position, which I already discussed briefly, but we also have the time, which I have not discussed, which changed at a rate of 0.033 seconds per capture. In addition, we have the gravity constant, like I discussed earlier, 9.8. We have B, which I also discussed, which was found using trial and error to see at which point would they match up, they being my observed and my computational data. So I had a trial and error in that, and I set this to 0.051, which gave me almost the exact same final point for my Y. In addition, you can see the formula for weight force. W is equal to the negative ball times mass times gravity. And we can also see the drag force equation. D is equal to negative B times the magnitude of the ball velocity squared times the normalized ball velocity. Finally, you can see the net force that is calculated by W plus D. And then at the bottom, we can see Newton's second law being graphed, as you'll see in the future. Here's some of the data. I'm going to go into it more in a second, but these are all of my data points. The first one on the left is my observed. The middle one is my observed without, or my computed, without drag. And the third one is computed with drag. As you can see, the observed and the computed with drag end at the exact same point. However, they have different routes to get there, which is what I discussed earlier with the errors. The computed without drag shows how much different the velocity changes, or the velocity changes for an object when drag is not factored in. So what does this mean? Well, the two different velocity graphs you can see here are with drag and without. And this is, of course, my computer model. The drag enforces a terminal velocity as air resistance cancels out the gravitational pull. Without drag means that the velocity decreases at a constant rate, which you can see in the graph on the right. What if? Well, the what if question is if the ball is thrown downwards, the initial volume, the velocity would obviously be greater, which technically is less as in my experiment, I used -3 on the y value to demonstrate, which you can see on the left. Theoretically, this would make the ball reach a terminal velocity quicker, but it's hard to see due to the light weight of my ball. But yeah, thank you guys for listening and watching, and I hope you have a great day. Bye-bye.